Welcome to part 4 of our exception handling lecture. So far, we've learned how to write clean try-catch finally blocks, create custom exceptions, and safely handle file operations. In this final section, we'll look at what happens when exceptions go unhandled, how to set up global handlers, and explore the .NET exception hierarchy so you can take full control of how errors flow through your application. Let's begin by reviewing how exceptions behave after a finally block and why rethrowing matters. Here's a classic rethrow pattern. In method 1, we throw a general exception, catch it, log it, and then use throw. To pass it up the call stack, using just throw without X is critical here. It preserves the original stack trace, helping you debug accurately. Always use throw when you're rethrowing an exception. If you throw a new exception, pass the original one into the constructor using the inner exception property. This helps maintain full context and traceability across layers of your application. When an exception is caught, execution continues after the finally block. If the exception is not caught or is rethrown, control moves up the call stack. So remember, finally always runs, but it doesn't stop the exception from continuing upward. An unhandled exception is one that isn't caught anywhere in your code. It propagates up the call stack until it hits the runtime, which then crashes the program. These can be dangerous but are entirely preventable with global exception handling. This simple example shows a method that divides by 0. Because there's no try-catch block, the exception bubbles all the way up and the program crashes. This is what happens when you don't handle predictable risks. A global exception handler acts as your last line of defense. It catches everything that wasn't handled explicitly. You can use it to log errors, gracefully notify users, or safely terminate processes. This is essential in production applications. In this example, we subscribe to the appdomain.unhandled exception event. If an exception escapes all try-catch blocks, this event triggers and logs it. It doesn't prevent termination, but it gives you a chance to log or alert before the program shuts down. In asynchronous or parallel programming, tasks may throw exceptions that go unnoticed. The task scheduler.unobserved task exception event lets you handle these background exceptions. Don't forget to call e.setObserved, otherwise the runtime may still treat it as unhandled. Here are your go-to guidelines. Wrap risky operations in try-catch, set up global handlers, always log exceptions, and never expose stack traces to users. Show friendly error messages instead. Remember, unhandled exceptions crash programs. Use appdomain, unhandled exception, and task scheduler, unobserved task exception. Always log the error with useful context. The goal is graceful failure, not silence or chaos. If no catch block handles the exception, the method terminates. Any code after finally is skipped. This is why it's critical to plan your exception flow. Don't assume the next line will execute after an error. Let's reinforce this. The finally block always runs. After that, control either returns to the next statement or the exception continues upward, depending on whether it was caught. You can use a generic catch park-pollers to handle any exception without needing to name it. This can be useful in highly generic handlers, but it's generally better to catch specific exceptions for clarity and control. Exception objects provide more than just a message. Help link, a URL to documentation. Source identifies the application. Target site, the method that caused the error. These help you diagnose problems faster. Two core properties of any exception. Message tells you what happened. GetType tells you what kind of exception was thrown. Use both to create logs and UI messages that are helpful but not overwhelming. In C#, all exceptions inherit from system.exception, system exception for system-level errors like null references. Application exception, originally meant for custom exceptions, but now discouraged. Understanding this tree helps you write better catch blocks. Here are some exceptions you'll see regularly. Divide by 0 exception, index out of range exception, null reference exception, Stack Overflow exception. These are built into the runtime and often indicate bugs. You can catch broader errors using base classes like system exception or exception. This is useful for fallback or logging logic, especially in global handlers. This code tries to access an invalid array index. Instead of catching the specific index out of range exception, we catch system exception, which handles a whole family of errors. This approach simplifies error handling for grouped scenarios. Application exception was intended for user-defined exceptions, but Microsoft now recommends you inherit from exception directly. It's cleaner, less confusing, and gives you better flexibility. This legacy example shows how to create a custom exception using application exception. Today, we avoid this. Instead, just inherit from exception and define your message and constructors. Java forces developers to handle certain exceptions. These are called checked exceptions. C# doesn't do this. All exceptions are unchecked, meaning it's your job to handle them voluntarily. This gives you more freedom, but also more responsibility. In Java, a method that throws an IO exception must declare it or handle it. C# doesn't require this. But just because C# doesn't force you, doesn't mean you should ignore exceptions. Handle them responsibly. To summarize, all exceptions in C# inherit from system. Exception use base classes when appropriate, but prefer specific catches when possible. Avoid application, exception in custom errors. C# doesn't enforce checked exceptions, but good developers handle them anyway. This concludes our final section on exception handling. We've seen how to handle both expected and unexpected failures, how to clean up resources, and how to control error flow across multiple layers of your application. From basic syntax to global handlers, and from system exceptions to your own custom types, you now have a full toolkit for building robust, fault-tolerant C# software. In our next topic, we'll begin exploring event-driven programming and delegates, opening the door to reactive, modular, and dynamic application design.